All right, good evening, everybody. Welcome back to vBrownBag. Tonight, we're going to hit a new topic, at least new to me, and maybe new to a lot of you who are watching this either live or recorded after the fact, data engineering. And we have AWS hero Elliott Cordo joining us tonight. Did I say your last name right, Elliott? Is it Cordo?
Yes, you did.
All
Hi,
right,
Lee.
awesome. So I'm going to hand it over to Elliott in just a moment here, but before we do, a few housekeeping notes. This show is being recorded live. If you're in our audience tonight, please remember, ask your questions via the Q&A, not chat, or you can just hit us up on Twitter using the hashtag vBrownBag. In fact, you can use that hashtag anytime. If you have any questions for anybody who's been on here, you could tweet them, you could use this hashtag. Or if you have a topic that you want to talk about sometime, you want to share your story, your knowledge with the community, hit us up. You can use the hashtag vBrownBag. You could tweet directly at me or the vBrownBag account. I'm Ken Nalbone. I'm at Ken Nalbone on Twitter or at vBrownBag on Twitter. Great way to reach us. This is our schedule on the right here as well. So if you're watching this on YouTube, you think you'd like to attend live, right now this is being recorded on the US show, which is 7:30 p.m. Central every Wednesday. We have other shows in other time zones and even other languages. So check out the one that's most applicable to you. So without further ado, I'm going to turn it over to you, Elliott. Let me hit the stop share button and you can take it away. All right, I see your screen.
All right. Good evening, everyone. Tonight, I'm going to take you on a whirlwind tour of data engineering. So a little about me. I've been doing data engineering for and backend engineering for about 2 decades, a little longer than I'd like to admit. Currently I'm working with Capsule, which is a digital company. It's a pharmacy that works for everyone. I'm also an AWS Data Hero, part of their community program. My experience ranges from big enterprise companies to small early stage startups, kind of helping solve mainly data engineering problems. So the purpose of today's talk is to really, kind of do an overview of data engineering, kind of demystify some of the terms that you might hear, give you an overview of what it actually takes to build a data platform, which is the main work of a data engineer. And we'll even talk about like some career pathing and to some specific personas in terms of folks that might want to change over to the data engineering profession. So this is really hopefully going to give people a comprehensive idea of what it's like to be an engineer. And I'm really covering things, both as a data engineer and also as a hiring manager. Like these are the sort of things that I'd want an engineer coming into my organization to know. So I think it's really useful. Hopefully you find it so, and hopefully you consider data engineering as a career. So first off, what is data engineering? I think, a lot of people would describe it in different ways. I like to describe it as plumbing. So we are plumbers, and being a plumber in data engineering is actually a pretty cool job. It's actually, pretty sexy, I feel, because what you're doing is you're taking like all these raw elements of data, all this raw data, and you're actually making something super valuable. Something that we call like a data product. So taking raw data, acquiring it, transforming it, and then storing it in a way that it's really valuable. And what are data products? So a very common product, or a very common kind of like endpoint of a data engineering exercise is going to be an analytic one. So you're thinking about like data lakes and data warehouses, building reports, right? And we're going to cover some of these things in detail later on in the presentation. But also like automating ML and data science pipelines, enabling marketing technologies, kind of functions such as revenue management, royalty calculation, even cash management. These are all like data products. Building a robust customer profile. And even CRM interactions, like building a customer relationship management system and getting all the data that's needed to really have a 360 of your customer. Like these are all like products produced by data engineering, and many more products. Tonight, we're mainly going to focus on the kind of most common kind of analytic products at the top. So we're going to talk a lot about like the data platform, and the reason we're going to focus on it is where the work gets done. So the data platform it should be considered that factory that creates those data assets that I just mentioned. So as a data engineer, building, maintaining, and integrating a data platform is where you're going to spend the majority of your time, building this platform, maintaining it, extending it, and kind of maturing the data platform, and using that to kind of manufacture these data assets. So as mentioned, I'm going to, most of this talk is going to be an overview of, kind of the components of the data platform and how it works. There's obviously a lot of ways to solve this problem, but I'm going to kind of base this on my experience and kind of my best practices when building such a platform. So, I'd consider this, a pretty good way to build a data platform and look at it. And I'm mainly going to talk about like 4 layers today. The first off being ingestion, which is how we acquire data from various source systems and get it into our platform. We're going to talk about like the landing area, also known as a data lake in a lot of implementation, where we're storing this data. Transformation, which is a really interesting part where we're going to do a lot of work and things get really, really complex. We're going to apply a business logic, clean, prepare data, and basically use that to build our target data assets. And then I'm going to talk about a serving layer, which is kind of the final state of our data assets. In this case, we are going to consider this data warehouse. In fact, a dimensional one with facts and dimensions. And I'll try to dive into each of these components and give you an idea of how we do these things. So first, we're going to start out with the first layer, which is ingestion. So ingestion is comprised of processes that help us acquire data, as the name would infer. And data platforms end up accruing a lot of data. I'd say like the average data platform I built probably had dozens of source systems, and in the end, probably thousands of tables and data sets that are used to power this platform. And these are going to come from two main types. So one is internal, so ones that you have control of. So you're going to be integrating with basically services and applications within your organization. And also external sources. And when I say external sources, I'm talking about SaaS platforms, such as your Salesforces of the world, or your NetSuites, or your Adobe Analytics, as well as partners when you're taking in data from other companies, or perhaps subsidiaries of your current company into your data platform, into your organization's ecosystem. So the target for ingestion is typically going to be, we call the landing zone of our data platform. And ingestion, at least in modern data platforms, has kind of a single responsibility of acquiring data, not transforming. And we'll talk a little bit more about that in coming slides, and kind of talk about like the history of how we've come to that conclusion, building modern data platforms.
So, Elliott, what are some of the kinds of data that we're talking about ingesting here? Are we trying to capture data just for the purpose of this data platform, or is it something that is already happening due to existing line of business apps? We figure how we can do something useful with that. Like, what's the genesis of this project of data engineering to begin with?
Yeah, so I think very typically, the data that you acquire is driven by like a business use case, right? So to keep it really simple, to use an example of like kind of sales reporting, right? Sales reporting would drive you to ingest data from several systems, maybe your internal systems, maybe you have some sort of like POS-like or ERP-like system, which is doing transactions with your customers, and that's all great. But maybe you need additional metadata from like a CRM in terms of like who these customers are, when they first joined with us, what channels they like to communicate, right? So and what channel we use to acquire them, right? Which might actually require you to use some analytics data, like which gives you kind of all that preceding information up to the time that they sign up. So I think like typically this is driven by business case. You don't usually go into an organization and say like, okay, let's just try to like funnel all of the data into your data platform up front. I think usually it's usually prioritized by what's needed and the use cases depending on what you're trying to achieve, reporting, customer relationship management, maybe even data that needs to be prepared and kind of normalized for like a machine learning project.
Cool, thanks. Yeah, that was a very good and thorough answer.
Great. So for the budding data engineers out there's really two ways that we get data. The batch ingestion is probably the most common and most traditional way to get data, and it's very easy to understand. It's a job. It's a job that basically acquires data from source system on some schedule. And this job would be scheduled perhaps once a day or even every few minutes. When you're running things like very fast and keeping very tight controls on kind of like incrementally acquiring the data, that's typically referred to as a micro batch. But in the end, it is a job that wakes up, gets data, and kind of goes back to sleep and picks up where it left off. So in terms of batch ingestion, some common sources that you're going to run into is probably the most common for organizations is a relational database, right? So the databases which underpin our applications, right? So many times, like when organizations develop their services, develop their applications, they aren't really thinking about like, hey, like somebody's going to need to get this data out in bulk one day. So as often the case, a data engineer is going to have to go and reach into that relational data, run some batch job that runs like a programmatic SQL statement, and then, basically fetches it, iterates it, and collects that data for storage in our data platform. And in other cases, either internally, like if those service owners and application owners decided that, hey, we want to build some sort of batch interface for people to collect data, we don't want them touching our databases, but more commonly, external sources, like if you're dealing with a Salesforce or you're dealing with a Amplitude or an Omniture or any of those kind of like externally hosted systems that you probably work with, you're typically going to go through an API. So you're going to be hitting some endpoint, walking it, either streaming the results down, or if it has pagination, kind of iterating those paginated results to collect data. As a data engineer, and these tend to be the more advanced cases, not always where you start, but real-time ingestion is also something that you may run into. And really this is a little different than batch. Instead of like kind of waking up on some cron or some schedule, you're basically acquiring the data as a steady stream. So most times, or it might be at least event driven. So I think the most easy or common use case for kind of real-time ingestion is going to be receiving data through some sort of messaging system. So, obviously a very common one is SQS, which is Simple Queuing Service from AWS, Kinesis, or even Kafka. So essentially you'd be placing yourself as an event consumer, reading that queue, and kind of pushing those kind of data sets down to your kind of landing zone or to your data application as soon as possible. Another example of real-time ingestion, which is becoming pretty common, is kind of like object storage. So Amazon S3 or Simple Queuing Service, essentially having data land there directly, either by your application owners or maybe even third parties, kind of landing this data directly to S3. And optionally, notifications can be triggered by Lambda to go and process that data. There's other examples out there of real-time architecture, kind of front-ending with an API in front of your data platform as well, kind of allowing people to push data in via webhooks. But in the end, it usually ends up in a queue. And the work of, kind of the data engineer kind of starts there. And again, the object storage, kind of S3 scenario is pretty common as well. So, just going back to the simple case, the batch job, there's many techniques and variations on this pretty typical approach, but you're essentially going to iterate a source, whether it's a relational database or it is a API. You're going to buffer it to memory or local, and you're going to store the data in landing. And there will be some sort of complexity to the storage strategy in landing that we're going to talk about as we get to the next section. So as a data engineer, what tools are you going to use? So this is, changed a lot over the past few years, I'd say the last decade. And a lot of the work has come back to code. So actually writing, jobs as software. And in the data world, Python has become a very popular framework, almost a monopoly on, managing that ingest layer. There's also, thankfully, a lot of tools that have come up on the market that have pre-built integrations to these external systems, especially when you're going outside. When you're going to the NetSuites and the Salesforce, there's a lot of complexity in dealing with those systems and dealing with their APIs. So there's a lot of systems that are new, what I call like new school, kind of ingestion systems or acquisition systems, as I'd call them. Stitch and Fivetran are good examples, and they give you basically managed pipelines of your data into your data platform. And many new SaaS applications are actually making it even easier, and much like I described in terms of like delivering data to S3, they magically deliver the data to your landing zone. So they kind of make the acquisition layer of this almost trivial, right? And there's even more stuff coming out in terms of even AWS and cloud providers creating integrations which allow you to easily acquire data from certain sources and internal services. So, as a data engineer, just one pro tip. I know that's pretty, kind of early in your data engineering career, or at least the consideration. Is avoiding undifferentiated work. We do have to write a lot of code, but there are a lot of ways of working with companies as well as tools on the market that will keep you from writing a lot of code that's better saved for more interesting layers of the data platform, which we'll talk about. So the next area we're going to talk about is the landing zone. So the landing zone is an area that stores all of your raw data. I think of it as kind of like the foundry, or kind of like I don't want to use warehouse too many times, but a warehouse for all those raw materials. And generally it's kind of immutable, meaning that we really try not to change data that lands there. And this is for a few reasons, and I'll talk a little bit about a paradigm shift that's happened in kind of data engineering over the past decade. So downstream processes can make mistakes. So if you actually take data and you process it, and you apply filters, you apply calculations before you land it to your landing area, you've now kind of propagated that mistake into your source data, and it can be very difficult to fix. In fact, some systems, like think about your a clickstream provider, is not going to maintain that data within their system forever, or might not be able to deliver it to you again. So you might have damaged data and it's unrecoverable. It's an irreversible mistake. Very similar thing is that even if we don't really manipulate the data too much, but we kind of like discard data and attributes that we don't need today, we're going to find that they might be helpful in the future. So again, like even if that data is recoverable, do we really want to reprocess it again to like project a few more columns or include a few more columns in our data? So again, like in the end, what we try to do is, keep our raw data relatively immutable, Once we write the data, we don't overwrite it. And kind of like this paradigm also has like a good collateral kind of improvement that we can observe changes. We can see the same data come in maybe as updates, and kind of it can be really interesting from a data engineering perspective to kind of compute the deltas. Like some of those things might be business events, right? Like a customer switching their home address, right? And getting back to like why this paradigm's kind of changed over the years is, and we'll talk a little bit more about this, is storage used to be expensive, and the only place that you could put stuff is a relational database. And since that's changed, our kind of attitude is storage has gotten cheaper. We have a lot of like interesting ways to store semi-structured data or really wide data. We've kind of changed that paradigm and kind of made, kind of acquisition in the landing area relatively pure. They have the responsibility of acquiring data and saving all data. So where are we going to store this data? What technologies are involved? So a very traditional way to do it, and sometimes it's the right solution, is good old relational database. Also known as like a staging area, or a ODS, which is known as a operational data store. And this scenario still makes sense if all your sources are relational and the data is small, right? If your environment is made up of Postgres databases and you decide to build a small Postgres like data platform or data warehouse, is a perfectly reasonable way to kind of manage this. But more generally these days, we are using a data lake approach, which is using an object store such as Amazon S3 to store our data. So for those of you who aren't yet huge Amazon S3 fans like I am, it is a simple service that does remarkable things. So S3 is an abbreviation for Simple Storage Service. And basically what it is it's a file system. It's an object store that can hold any type of data, structured or unstructured, and it's highly available, durable, and performant. And best off, it's inexpensive. And it's integrated with a lot of AWS services. So again, coming back to like how we ingest data and kind of notifying on arrival and triggering other processes, this stuff all comes for free. And I think for those of you who kind of remember big data and the word Hadoop, like the thing that made Hadoop famous was HDFS, which is functionally very similar to S3. It's a really important foundational building block from most systems. Or in other cloud providers, whether you be on Google or Amazon, they're equivalent, or Azure, they have equivalents as well. So file system, data lake seem really easy. I will not, kind of use the data swamp analogy, but instead I'll talk about like what you should do if you're gonna have a data lake. It's important to keep things organized and performance. And the things you want to think about are bucket and key structures and partitioning schemas, which I'll talk a lot about. And the reason we want to do this stuff is, organization helps in regard to data discoverability, right? So if you have really well-defined kind of like naming conventions and structures and subfolderings, or as it's called in S3 keys, you can make the data really accessible to downstream processes, whether it be data science or that downstream data warehouse. Again, like things like partitioning schema can have a really positive effect on performance. So to give just a really quick example, I have this S3 bucket. It's my internal landing bucket for my org. So maybe my org's internal data, not partner data, not third-party or SaaS data. Within it, I have some sales data. And that sales data has been partitioned, the DT equals, and then year, month, and date by date. And depending on how the data arrives, what's most optimal from a performance perspective, you could be placing your data, your files, inside this date partition, either by the time it arrived, which is most common, or perhaps like even a business date, which is a little harder, but sometimes it makes a lot of sense. And really the beauty of this is, other than like, hey, discoverability, like I know exactly what I'm looking at. I'm looking at my org sales data, and I'm looking at it for particular dates and date ranges, is that the tools that sit on top of this, right, whether it be your kind of data warehouse or a big data query engine or even Apache Spark, can interpret this date as a virtual column, and actually you can use it in your SQL statements. And aside from being convenient, what this does is it actually helps limit the amount of data that's scanned within your kind of data lake. So less data scan means faster and more performant. So in this case, we're only going to grab those subfolders or read the data from those subfolders that exist from 2020-0101 to 2020-0301. That was the only good part of 2020, by the way. So
we all did learn how to make sourdough starters too. So
that is true. Yeah. So another important thing, that we're diving into, like the data lake, which we thought was going to be really simple, like just this file system that we keep thing, is file formats. And I think we're familiar with some of these, like the CSV. Everybody's familiar with that. It's a save as from Excel. That's actually the worst. We try not to store data in CSV format. In fact, going back to what I said, we try not to transform or change data much. If we get data in CSV, sometimes we make the decision to actually do a file format conversion because it's such a pain. And why? You add a column, you break something downstream. You change the definition of a column, you change the order of the column. It's just really like fallible from like a schema perspective. JSON's way better. It's actually great functionally. It's self-describing. It supports semi-structured data, like a lot to like about JSON. But really within our landing area and data engineering, we work with unique file formats. Columnar formats are probably the most popular. The two most popular are Parquet and ORC. And the reason we like them is when you line up data, and I should add a diagram for this, column-wise, rows start, like columns across rows look pretty similar, right? So as you think about, kind of if you can compress that data, when things look similar, when data looks similar contiguously, it compresses better. Since data across columns usually looks pretty similar, there's all sorts of like really good compression algorithms that can be run on these files to make them smaller. And smaller means faster, less data scanned. And they also have some really interesting characteristics of only having to read or process the columns that you are actually using in queries or loading programmatically in your process. And then there's these new school file formats, Hudi and Delta Lake, which you can do some research on. And just safe to say that they do all the things the columnar file formats do, but they actually enable database-like behavior. So imagine being able to do updates and inserts on like massive amounts of files. Really cool technology, solves other engineering problems too. Just things to be aware of. And also to kind of illustrate that this kind of like landing zone actually requires a good amount of architecture and engineering, even though in the end we're just mainly storing files. So the next thing we're going to cover is transformations. So transformations is really like the factory. This is where we turn data into gold. We're really making sure that our data is delivering value. So the work that we're putting in here is data cleansing. We're taking data, we are removing inaccurate values, we're standardizing things. Something as trivial as a phone number. We're trying to get rid of duplicates of transactions, duplicates of people. Not really get rid of them, but just take them out of our reporting. We are enriching the data, so we're maybe joining that data with other data sets to improve its quality or maybe add attributes. Like again, going back to that customer record, like by joining the maybe clickstream data, we can kind of enrich it and maybe get like the channel that they came in with us or how many times they used the website a week. combining disparate data sources. An example there, I think like if you look at, if you've been a data analyst and, like kind of looking at raw data, you're going to end up joining together like, 10 plus tables and things aren't quite compatible. What we're doing is we're doing all that work up front, so that the work can be easier on the analysts and the consumers downstream. We're creating custom attributes, we're creating calculations, we're embedding business definitions and logic, we're aggregating, and we're also loading to the serving layer, and much, much more. So how does all this magic happen? We currently these days use a process called ELT, which is extract, load, and transform. And this kind of acronym traverses acquisition of acquiring data all the way through transformation. And going back to an older paradigm, which you might have still heard about, which is ETL, which is extract, transform, load. And just by definition, you've kind of realized some of the things that I mentioned before in terms of having single responsibility, acquiring data, landing data, and storing data immutably in a safe place. The transform in the middle leads to those problems that I spoke about before, which is, hey, what if you got a calculation wrong? Hey, what if you remove some data that you will find useful in the future? So ELT has become, kind of the paradigm for modern data platforms, and T is what we're really specifically talking about here. Much like acquisition, we're writing jobs as software. And generally, we're using much SQL. I know there was like a period years ago where we felt like SQL was in its end of days, but SQL is strong. And a lot of these transformations are being expressed in SQL, even if we're using like some high-tech technology, such as Apache Spark. And we'll talk more about that. We'll talk more about that when we get into kind of like some of the career personas and the things to think about. Another thing is that if this is a data warehouse use case, typically this T and this transformation is typically happening in the target platform. So if we have a Postgres data warehouse, we are doing our transformations probably in that Postgres data warehouse. If we are using a kind of MPP, massively parallel processing, distributed data warehouse like Amazon Redshift or Snowflake, the transform is happening there. We are using that horsepower under the hood generally. So the frameworks we're using, plain old SQL scripts. Maybe we are cloning, in a very simple case, maybe we're cloning some stuff through pSQL. Maybe we are wrapping this in code to do some programmatic manipulation of the SQL. Using good old PsychoPG2 for you Python users. And luckily, like tooling is starting to, evolve. We have a database build tool, also known as DBT, which has given us a framework that a lot of organizations are using and standardizing on, which basically gives us a more modern modular approach to performing transformations in plain old SQL and removing a lot of the boilerplate and kind of like framework that people are doing to kind of do transformations on their platforms. So another kind of meme that I will spare you guys from is the big data. I only talk about large data. For larger data sets, sometimes we don't do this work on the target platform, on the data warehouse, on the Postgres, on the Snowflake, on the Redshift, and we are going to leverage an external platform. It isn't necessarily always for a larger data set. It might be that we want to kind of like the complexity of the transformation we're doing, or maybe we want to map some sort of like ML model against our data. Then we may use an external platform or an external framework, leveraging our data lake, and we can use our framework of choice. And very often these days, it's Spark. But also if it's just the SQL transformation that we just want to scale and take weight off of our data platform, conserve our compute resources, we might be using Presto. We might be using Flink, especially if we're doing like real-time use cases. There's some interesting properties of Flink that allow you to do very cool things in both batch and real-time modes. And of course, good old Hive, which has survived kind of the big data, revolution and its evolution. It's still around and still quite powerful if you are, kind of processing large data sets. Lastly, we're going to talk about the icing on the cake, which is a serving layer. So the serving layer, I like to describe it, as kind of an API for your data products. And it might not always be an API, but I like to consider that serving layer this way. And it can take a lot of forms, like depending on what you're building, your endpoint could be an API. It might be as simple as like a data set that we're sending out to some partner or to some external system. And many times it's a data warehouse, which has been like kind of the story we've been following through this presentation. So the data warehouse, if you're going to be a data engineer, is likely something that you are going to encounter. And basically the concept behind a data warehouse is that we're storing data so that folks in your organization can access large amounts of data. So if you had 20 source systems and dozens of services and external stuff, this data will all be in one place and they can have access to it in full history. It should be easy to use. So generally, although we're landing and storing this data in kind of like our landing area, we are doing all that transformation that we talked about in the processing layer, and making the data easy to use, like exposing derived data sets to people. We're putting value into this. We're not just exposing raw data. And we're making it so that it has a lot of governance, it's secure, it's reliable, it's durable. And these sort of systems like find a lot of utility for data analysts, of course, like people who are going to build reports, people want to analyze data, they have a lot less work to do. The work is going to be more repeatable, less error prone. They're going to have a single source of truth. But it turns out that these data warehouses end up being part of, a larger data platform often where they're a target, but also, because the data is clean, a lot of things are being brought together and kind of assembled in such an efficient way. It ends up being useful for other things, like very popular with data scientists. This may be the thing that feeds some of those downstream systems, such as your CRM, your marketing technology systems, and many more. So there's many schools of thought on how you build data warehouse, and some would say there's no wrong way. I am maybe a little old school, but I still like this concept of the star schema. There's some very traditional approaches to this. There's what you probably hear is the Kimball methodology, which is very rigorous, very artful, very aesthetic. But today we primarily practice a variant of that, in a lot of the organizations I've been a part of, and kind of my personal style, which is basically a modern pragmatic version of the star schema. So for those of you not familiar with a star schema is just a way of modeling your data. Like these are tables. Like we are creating tables that are derived and very simple. And, at the center of most star schemas is a fact table, like an event table, which has like kind of your metrics for your business. So this could be your sales fact. This could be a fact about communication. So, all the events that, you kind of reached out to somebody through SMS or email marketing. It could be, kind of contract transactions. It could be, kind of usage of goods. So anyway, any data warehouse is going to have many of these facts. They're all going to be kind of, the verbs of your organization, the events. And then you'll have a bunch of conformed dimensions, which you kind of build once. You build a customer table once with all of the beautiful attributes you might like. and then that's reusable through your data warehouse, and what you end up with is a bunch of stars. You know, it's again, like, it's primarily a modern pragmatic approach. You know, if you do decide to dive into like kind of Kimball and kind of understand what that's all about, the reason we don't do a lot of that stuff anymore is because that is quite an old way of doing things. It actually goes back to like relational databases and, you know, more primitive relational databases. Modern data platforms, it's fine to kind of like flatten things and make things really wide and have like, you know, a fact table or a table with like maybe 100 or more columns. Store strings instead of integers. Like, storage is cheap. You know, platforms and MPP databases have really evolved. So we've gotten a lot more simple, which you know, makes building these things a lot more productive as well. So if you're going to build a data warehouse, like, where do you do these things? Like, what, you know, I mentioned a few technologies such as like relational MPP. Again, like, if you have a really small, like, kind of shop, you know, you're an early stage startup, like, you know, maybe a relational database is going to make sense. It might be that same, it's probably going to be that same database that you built that kind of relational landing zone. But more generally, you know, people are using what are called like these MPP databases, which is massive parallel processing. And what this is, you know, rather than having like a single server, a single like kind of relational database that you can only like scale up, MPP databases essentially are like a cluster of machines. So instead of, you know, kind of buying bigger and bigger machines, you just keep adding machines to your cluster. You can store and process more and more data, which is generally like kind of a modern engineering paradigm. You know, you eventually run into like the biggest machine you can buy, and then you're in trouble. When you scale out, you know that you can store and process as much data as you need to. And you know, the popular choices are, you know, Redshift and Snowflake, both great platforms that I've worked with. You know, you know, these are very popular services for building a data warehouse. And then other times, you know, you might build your data warehouse directly on your data lake. So that transformation layer might be in the data lake. Your serving layer might be in the data lake as well. I think, you know, typically you see kind of a S3 or kind of like data lake approach to data warehousing, usually when data sets are really, really large. So if you're like in an ad tech company or a media company and you're just generating like huge amounts of data and the data is largely immutable, I would say it's sometimes less complex in some cases, but I don't want to use that as a rule. You may see a data warehouse built directly on a data lake. And there's obviously like a lot of architectural considerations and decisions, you know, if you're going to go down that route and if you have that requirement, much like some of these other platforms. But, you know, the data lake is also a suitable data warehouse for your organization in many cases. So lastly, do you want to be a data engineer? So I'm gonna like kind of talk a little bit about this, kind of putting on like my hiring manager and coaching hat, and kind of give you guys an idea of what I look for and maybe some suggestions. So, you know, if you were to like kind of go over this presentation and kind of grep all the things that we've been talking about, this is kind of like the skills recap, and probably like not on purpose, probably matches like some of the requirements that you'd see in a job rec that I personally wrote. So, you know, I think the first one is an interesting one, which is analytical and business aptitude. You know, so like, this is not a pure technology thing. I think the fact that like when you're building an analytics system very often, especially a data warehouse, you're actually like imprinting, you know, kind of business processes and you know, kind of business definitions and kind of like the language of your business into you know, the thing that you're building. So really having like kind of understanding from an analyst perspective as a user, and also really understanding your business is really super helpful. So somebody who, you know, kind of, you know, understands the role and is willing to kind of dive in and kind of understand the business and business processes. strong working knowledge of a mainstream programming language. Again, Python is very popular. You know, listen, there's probably lots of Go shops out there and people doing this in Java as well, but Python is probably the majority of the kind of data domain. Strong SQL skills. So as I said, SQL won when it comes to data engineering even over the past couple of decades where we've seen a lot of innovation. So really, really strong SQL skills. You know, the ability to kind of manipulate data, use analytic functions and windowed functions. Really kind of complex crunching. Just really, really like level 10 SQL Ninja skills. And a working knowledge of the public cloud, because much like any modern application, the infrastructure and the kind of like code and the system are all kind of like one thing. So like, being able to make intelligent choices about the way you implement things, kind of understanding the features of the services that you're using and characteristics of the services you're using in the public cloud is really important. So in my career, like other than people that I've hired that had the title data engineering and been doing it for a while, there were, I'd say like, plenty of exceptions, of course, but I'd say like the two most prevalent personas that kind of transferred into data engineering were that of like kind of a data analyst or even a SQL developer. So especially for data analysts, they have like kind of that analytic point of view, right? Also probably know a lot about like their business, or at least have been challenged, if it's a new career, been challenged to kind of really understand the business. So really having that willingness. Where they might be lacking is Python, right? And that's really what I encourage. Like if you're interested, if you're a SQL developer, a data analyst, improve your Python skills. And it doesn't necessarily need to be super data analytics specific. Learn Python as a generalist. For our project, you can flex your Python skills. And if that's playing with a Raspberry Pi, if that is developing an API, that is totally fine. Just learn the language, understand how it works, understand the data structures, and the basics, right? And if you're a backend engineer, this is also like one that's really great. They have like a strength more on the infrastructure side. They're probably going to know the cloud a little bit. They're also going to have like that rigor, that like kind of professional engineering background. Like they're going to understand CI/CD. They're going to understand, appreciate unit tests. They're going to understand, how to build applications well. Great stuff. Where they may be lacking is probably like that analytical point of view, and they're probably not as good as SQL as they think they are, right? A lot of folks are using ORMs, and you should use ORMs, right? Object, what do you call it, like modeling. Handcrafted SQL is probably something that they're even discouraged from doing. So, really learn SQL, learn how to do it, as an analyst, and try to take on an analytical project. This is where, might challenge you to try to, do some tutorials, maybe try to wrestle with a Kaggle project, try to do something to kind of get you in that mindset of analytics and brush up and improve those SQL skills. And that is all I have for this evening.
Well, awesome. Thanks very much, Elliott. I was going to ask you, if people need to reach out to you, how can they? And you just put it up on screen. So folks watching this, make sure you take note. Find them on LinkedIn. Find them at Capsule. Thank you very much for joining us tonight, Elliott. Really appreciate it. I learned a lot of new stuff, and I know the people who joined us who are going to view this on YouTube are going to learn a lot as well. So just one final question for me. How do you determine what counts as data engineering and what is something else? And I'll give you like an example that has some elements of what you talked about tonight, but was not really probably as in-depth. So like I'm thinking back 15 years, I was a lot younger and a lot more naive. I guess I was a system administrator at a financial services firm, and I worked really closely with our single application developer. And like we got basically some data on a nightly basis from one of the financial institutions we work with, just a flat file. a record of transactions of the day. And some people in our operations needed to run reports on them. So we figured out how to actually push it into a SQL database in a format that made sense. We created a report that would run for them periodically, like weekly or monthly or something like that, based on just, what to them was indecipherable. And they thought it had value in it, but they had no idea how to get it out. Did we do a data engineering, or is it a little more involved in
No, I think you were a data engineer.
that? I didn't even
So
know.
you didn't even know it. So like, listen, I think like there's listen a ton of like subspecialties, obviously, like from ML engineering and so on and so forth. But there, I think the thing that's really interesting is that there is like kind of like almost a, if you look at the Venn diagram between like backend engineering and kind of like data engineering, there's a good amount of overlap. I think data engineering is going to index a lot heavier on kind of like those backend jobs, who's ingesting data, processing data, so on and so forth. Backend engineers sometimes do this stuff and like they don't think too much about it, right? But from a specialty perspective, they're probably more focused on building applications and building APIs and building services. Whereas the data engineer index the other side. They might build an API, they might build some internal tool or system to kind of like make their platform more efficient or solve some use case, but most of the work is kind of in that crunch from acquisition to final data product. And you made a data product, that report.
How about it? Well, cool. Well, thanks very much, Elliot. Really appreciate you coming on tonight. And we will say goodnight to everybody, unless there's any last questions, but I think we're good. And let's see if they come in. So thanks very much, everybody.